There is a question that has followed human beings for as long as we've been able to look up and wonder. It's not a complicated question. You don't need a telescope or any special knowledge to ask it. Just a quiet moment and a willingness to let your mind stretch a little further than usual. The question is simple. How big is all of this? How much space is really out there? And how does the place we call home, our galaxy, the Milky Way, compare to everything beyond it? Tonight we're going to wander through that question together, slowly, gently. Not to overwhelm you, and not to turn this into a lesson, but to build an understanding piece by piece until the universe feels a little more familiar. If you've ever stood under a clear night sky and felt that quiet mix of wonder and smallness, then you already know where this journey begins. Because that feeling isn't just in your thoughts, it's something you feel in your body. And the more clearly you begin to see the scale of the universe, the less distant it may start to feel. After all, you're not outside of it, you're inside it, made of the same atoms that have moved through stars for billions of years. So wherever you are, take a moment, let your breathing slow just a little, and let's begin. For a long time, scientists believed this portion of the cosmos was well understood. The Milky Way had been mapped, at least roughly. Its general shape had been inferred, its size had been estimated, the solar system had been placed within it. And for a while in the early 20th century there was a prevailing sense that the Milky Way might simply be the universe itself, that everything we could see was everything there was. Then new observations introduced details that didn't quite fit. Light from distant spiral-shaped clouds, which had long been assumed to lie within our galaxy, turned out to be travelling from incomprehensibly further away. The numbers, when properly calculated, pointed not to nearby structures within the Milky Way, but to entirely separate systems, entire other galaxies, each containing hundreds of billions of stars, each enormous in their own right, and yet so far away that all of that immensity collapsed into a small, faint smudge of light visible only through a powerful telescope. That discovery, confirmed in the 1920s by an astronomer named Edwin Hubble, changed everything. Not just the textbooks, not just the calculations. The entire human sense of scale had to be revised, expanded, stretched to accommodate a universe that was suddenly and undeniably far larger than anyone had seriously imagined. And what's remarkable is that the revision didn't stop there. The more carefully astronomers looked, the more they found, and the more they found, the bigger the universe became. So here is the first thing worth holding in mind as we begin tonight. The question of how big the universe is compared to our galaxy is not a settled question that science has quietly filed away. It is an active, ongoing, richly layered investigation that has consistently surprised even the people asking it. Every time we found what we thought was the edge of something, there turned out to be more. And rather than being a source of anxiety, that pattern has become, for many who study it, a source of deep and steady wonder. Because it means the universe has never stopped being interesting. It has never stopped being more than we thought. Now, before we go further outward, we need to establish something closer to home. We need to understand where we are starting from, and that means spending some time with the Milky Way, not as a vague glowing band in the night sky, but as the actual concrete physical structure that contains our sun, our solar system, every planet, every moon, every comet and asteroid we have ever observed, and every human being who has ever lived. You live in a galaxy. That word is so familiar it has almost lost its meaning. Let's give it back some of its weight. Imagine for a moment that you could somehow step outside the Milky Way entirely, not travel through it, but step back far enough to look at the whole thing from a distance, the way you might step back from a painting that was too close to see properly. From far enough away, what you would see is a spiral galaxy, a flattened disk of gas, dust and stars, shaped roughly like two fried eggs pressed back to back, widest in the middle and thinning toward the edges. From the side it looks like a lens. From above or below it looks like a pinwheel. a central bulge surrounded by long curving arms that sweep outward, glittering with stars, each arm a river of light. The disk itself stretches about 100,000 light-years from one edge to the other. Some recent measurements suggest it may be slightly larger than that, perhaps closer to 120,000 light-years, with the outer edges of the disk warping a little, curling up and down in a shape astronomers have compared to the brim of a bent hat. But for our purposes tonight, 100,000 light-years is a good working number. It's the number that will help us understand just how vast our home already is, before we even begin to compare it to anything beyond. A light-year is the distance light travels in 1 year, and light moves at nearly 300,000 kilometers per second. In a single second, a beam of light travels a distance roughly equal to going around the Earth 7.5 times. In 1 year, that beam covers about 9.5 trillion kilometers, so 100,000 light-years, the width of our galaxy, is roughly 950 quadrillion kilometers. That is a number so far beyond everyday experience that it essentially communicates nothing at all to the nervous system. It doesn't land. It doesn't feel like anything. So let's try a different approach. If you could travel at the speed of light, the absolute maximum speed that physics currently allows, and you set off from one edge of the Milky Way intending to cross to the other side in a straight line, you would not arrive during your lifetime. You would not arrive during the lifetime of any civilization that has ever existed on Earth. You would arrive, if everything went perfectly, in 100,000 years. The Roman Empire would feel recent. The entire span of recorded human history would feel like a brief opening chapter. And you would still be inside our own galaxy, having gone nowhere, by cosmic standards, at all. That's where we live, that's home. Inside this structure, our sun sits in what astronomers call the Orion Arm, one of the secondary spiral arms of the Milky Way. We're not at the centre, and we're not at the outer edge. We're somewhere in between, about 27,000 light-years from the galactic core, orbiting it slowly the way a planet orbits a star. Slowly is the operative word here. One full orbit of our solar system around the centre of the Milky Way takes approximately 230 million years. That means that in the entire span of time since the dinosaurs dominated life on Earth, our solar system has completed exactly one such journey, one loop, and the galaxy has been spinning for billions of years, which means it has made many such rotations without us here to notice most of them. At the very centre of the Milky Way sits something that scientists spent decades hypothesizing about, and only recently confirmed with direct observation. There is a supermassive black hole at the heart of our galaxy known as Sagittarius A star. It contains roughly 4 million times the mass of our Sun, compressed into a volume smaller than the orbit of Mercury. For years, astronomers tracked the motion of stars in the galactic centre and watched them move in ways that could only be explained by the presence of an enormous invisible mass. The movements were too fast, the orbits too tight, the gravitational pull too extreme for anything else to explain it. In 2022, a collaboration of radio telescopes called the Event Horizon Telescope released the first actual image of the region around Sagittarius A star, a glowing ring of superheated gas and dust circling a region of such intense gravity that not even light can escape. The dark shadow at the centre of that ring was the closest humanity has ever come to seeing a black hole directly. Knowing that such an object sits at the centre of your galaxy, right in the middle of our home, might sound unnerving, but it is worth remembering that at 27,000 light-years of distance, Sagittarius A star exerts no meaningful influence on our solar system's daily life. It is there, quietly, the way the deep ocean floor is quietly beneath every surface wave. It shapes the large-scale structure of the galaxy without reaching into your daily experience. And in a strange way, understanding it makes the galaxy feel more like a living thing, something with an interior, a history, a kind of deep architecture that goes far beyond what the eye can see. Around the disk and its central bulge, there is another component to the Milky Way that most people never think about. It's called the halo, a vast, roughly spherical region that extends far beyond the visible disk in every direction. The halo contains ancient stars and globular clusters, but more importantly, it is thought to be filled with something we cannot see at all. Dark matter. This is not matter that happens to be dark the way coal is dark, or the way the space between stars is dark. Dark matter is a form of mass that does not interact with light in any way that we can detect. It casts no shadow, it emits no glow, it leaves no trace in any optical telescope. And yet without it, the Milky Way would not hold together. The stars in the outer disk rotate faster than they should based on the visible mass alone, and the only explanation that fits the observations is an enormous invisible halo of matter exerting gravitational force. Most of the Milky Way's mass, by some estimates, is this invisible component. So when you think of our galaxy, the picture is always slightly incomplete. What we see is only part of the story. The disk, the arms, the bulge, the halo we can observe, these are the visible parts of something much more complex, like the exposed portion of an iceberg floating in a sea of dark matter that extends further than our measurements have yet been able to fully trace. This is already extraordinary, and we haven't even left the Milky Way yet. Let's try, for a moment, to hold the Milky Way in something resembling human scale. Imagine, as a thought experiment, that you could shrink the entire Milky Way down to the size of a dinner plate. Not a large plate. An ordinary dinner plate, roughly 30 centimeters across. At that scale, our entire solar system, the Sun, all 8 planets, the distant reaches of the Kuiper Belt, the vast cloud of comets that surrounds it, would be smaller than a single bacterium, invisible to the naked eye, smaller than the sharpest pencil point you could draw. The solar system, with all its planets and moons and the nearly 5 billion kilometers that separate the Sun from Neptune, would not even register as a mark on the surface of that plate. And the plate itself, your dinner plate-sized Milky Way, sitting on that table, represents home. It represents everything we have ever directly explored, everything we have ever sent a spacecraft through, every star we have ever examined closely, every planet we have ever photographed. All of it is too small to see, somewhere on that 30 centimeter disk. Now consider that the observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, extends not 30 centimeters, but something closer to the distance between London and Dubai. On the same scale where the Milky Way is a dinner plate, the observable universe is roughly 6,000 kilometers wide. Our home galaxy, the vast structure that takes 100,000 years to cross at the speed of light, is a single plate lost somewhere in a stretch of space that spans from one side of a continent to the other. That comparison deserves a moment. Please don't rush past it. The Milky Way is not small. It is almost incomprehensibly large by any measure that applies to human life. And yet relative to the universe that contains it, it is a crumb. A single grain of sand on a beach that extends as far as the eye can see in every direction. A single note in a piece of music that lasts for years. The relationship between our galaxy and the observable universe is so vast in its proportions that even the word vast begins to seem inadequate. Astronomers working with these numbers eventually reach for a particular kind of phrase. They describe the Milky Way as occupying roughly 1 part in 900,000 of the observable universe's diameter, which is to say, if you cut the observable universe into 900,000 equal strips and measured one of them, that strip would be about as wide as the Milky Way. That fraction, 1/900,000th, is the ratio of our home to the cosmos around it. And yet, here is something that is easy to lose track of when the numbers grow this large. The universe, for all its incomprehensible scale, appears to follow the same physical laws everywhere within it. The same mathematics that governs the behaviour of atoms in your body also describes the motion of galaxies a billion light years away. The gravity that holds the planets in orbit around the Sun is the same force that binds stars to their galaxies and galaxies to their clusters. The universe is not a lawless expanse, it's a structured one, and that structure, even at scales our minds were never designed to handle, is knowable, at least in principle. We can measure it, we can describe it, we can map it slowly, imperfectly, with the tools we have built for exactly this purpose. That is one of the most quietly remarkable facts about human beings. We live on a small rock orbiting an ordinary star in the outer regions of a mid-sized galaxy that is itself dwarfed by the universe around it, and somehow we have figured out how to measure the distance to the edge of what we can observe. We have found ways to read the light from objects so far away that they have been receding from us for almost 14 billion years. We have built instruments sensitive enough to detect the faint afterglow of the Big Bang itself, now stretched into microwave radiation, so gentle and diffuse that it fills the sky equally in every direction, like a cosmic whisper from the beginning of time. That whisper is called the cosmic microwave background. It was discovered by accident in 1965 when two engineers at Bell Labs in New Jersey noticed a persistent, irritating hiss in their radio antenna that they couldn't explain. They checked everything. They removed a pair of pigeons that had made a nest in the antenna horn and cleaned up what they diplomatically called white dielectric material. The hiss didn't go away. It was coming from the sky, from every direction equally, and it turned out to be one of the most significant discoveries in the history of science. The faint, ancient light of the early universe, cooled by billions of years of expansion into a soft, low-energy microwave hum. The universe was not always the vast, dark, cold expanse we observe today. It began in a state of extraordinary heat and density, and that beginning left a mark on the sky that we can still detect, still measure, still study. We are surrounded, literally, by the light of the Big Bang. It is behind every star in the night sky, behind every galaxy we can observe, filling the universe like a membrane of ancient warmth that has been cooling for 13.8 billion years. And inside that membrane, separated from it by almost the entire history of cosmic time, sit the galaxies, 2 trillion of them by some recent estimates, each one a collection of hundreds of billions of stars, each one enormous, each one separated from its neighbours by distances that dwarf even the galaxies themselves. You've probably heard the phrase light year before. It comes up often in conversations about space, in documentaries, in casual references to the night sky. But there is a particular way of encountering the concept that can shift it from an abstract unit of measurement into something that lands with a little more weight, something that actually changes how the stars look the next time you stand outside. Consider the moon, which is about 380,000 kilometers away. Light from the moon reaches your eyes in roughly 1.25 seconds. When you look at the moon, you're seeing it as it was a little over a second ago. The surface you're looking at, the craters and plains you can just make out on a clear night, existed in the state you're perceiving about the time it takes to take a single breath. That's how close the moon is in light travel time. The sun is much further. Light from the sun takes about 8 minutes and 20 seconds to reach us, which means that when you look at the sun, which please don't do directly, you're seeing it as it was 8 minutes ago. If the sun were to suddenly and catastrophically change in some drastic way at this very moment, you wouldn't know it for 8 minutes. The information travels at the absolute speed limit of the universe, and it still takes nearly 1/10 of an hour to cross the distance from the sun to your eyes. Now extend that outward to the nearest star beyond our sun. Proxima Centauri, sitting at a distance of roughly 4.25 light years, is our closest stellar neighbour. When you look at it, and it's visible from the southern hemisphere though too faint to see without binoculars, the light entering your eye left that star more than 4 years ago. Whatever is happening there right now, you won't know about for more than 4 years. It may have changed. A planet in its system may have experienced a storm or a quiet morning. you're receiving a delayed transmission, the way you might receive a letter from a friend who lives far away, written 4 years before it arrived in your hands. Go a little further, say to the bright star Sirius, which lights up winter skies in the northern hemisphere with a blue-white brilliance. That light left Sirius about 8.5 years ago, 8.5 years of travel time across roughly 81 trillion kilometers just to land in your eye on a clear night. And Sirius is considered nearby, in the context of our galaxy. The stars you see on any given clear night are mostly between a few light years and a few hundred light years away. When you look at the Orion Nebula, that faint blurry patch below the 3 stars of Orion's belt, you're seeing light that set out 1300 years ago, around the time the Islamic Golden Age was beginning on Earth, long before anyone then alive could have imagined the world you're living in tonight. The hazy band of the Milky Way itself, that soft river of light that crosses the sky on exceptionally dark nights, is a view across tens of thousands of light years of distance. The light making up that band has been travelling toward your eyes for thousands of years, some of it for tens of thousands of years, and all of it, every photon from every star you can see with your naked eye, is still within our galaxy. Everything visible to the unaided human eye, with the exception of a few nearby galaxies under exceptional conditions, is local. It is ours. It is home. And yet home is already unimaginably vast. So when astronomers start talking about the distance to the Andromeda Galaxy, our nearest large galactic neighbour, 2.5 million light-years away, they are stepping outside that home for the first time. When they discuss the clusters and superclusters of galaxies that stretch across hundreds of millions of light-years, they are mapping neighbourhoods so large that the Milky Way becomes unremarkable in them, as individual as a particular grain of sand on a long beach. And when they describe the observable universe in its entirety, stretching more than 90 billion light-years from one apparent edge to the other, they are describing something that the human brain was genuinely never designed to comprehend. That is not a reason to stop trying. It is in a way an invitation to sit with the incomprehensibility itself for a while, and notice what happens when you do. One of the great challenges of studying the Milky Way is that we can't step outside it. Every observation we make of our own galaxy is made from a point deep within it, the way you might try to describe the layout of a forest from within it, unable to see its boundaries, estimating its size by the density of the trees, and how long it takes to walk in one direction without reaching the edge. Astronomers have spent more than a century doing exactly this kind of inside-out mapping. Using the movement of stars, the distribution of gas clouds, the brightness of particular types of stars whose luminosity is well understood, and more recently the astonishing detail provided by the Gaia mission of the European Space Agency, which has mapped the positions and motions of more than 1 billion stars with unprecedented precision, scientists have assembled a picture of the Milky Way that is now quite detailed, though still with significant unknowns around its outer edges and in the regions hidden behind the dust of the galactic plane. What they have found is a galaxy with a structure both simpler and stranger than you might imagine. The disk, the flat, circular part of the galaxy where most of its stars and gas reside, is not perfectly flat. It has a warp. The outer edges of the disk curve upward on one side and downward on the other, the way the brim of an old hat might droop at the edges after years of wear. The cause of this warp is still being discussed, but it may be related to the gravitational influence of the large and small Magellanic Clouds, 2 smaller galaxies that orbit the Milky Way like satellites, and which are close enough to exert a tidal pull on our disk. The spiral arms of the Milky Way are another source of ongoing investigation. We know they exist. We can trace them by following the distribution of young, hot blue stars and the dense clouds of hydrogen gas from which new stars are forming. But the exact number and arrangement of the arms has been revised several times as new data has become available. The current picture suggests a galaxy with 2 primary arms, named Perseus and Scutum Centaurus, and several secondary arms and spurs, one of which, the Orion Arm or Orion Spur, is where our solar system resides. The spiral arms are not walls or solid structures. They are more like density waves, regions where the disk's matter temporarily piles up as it passes through, the way traffic on a motorway sometimes slows into a particular stretch, not because of any physical barrier but because of patterns in the flow. Stars pass through the arms over millions of years, entering a region of higher density where star formation is triggered, where supernovae blast apart old stars and compress nearby clouds into new ones, and then gradually moving out the other side and continuing their orbit in quieter space. Our solar system is currently in one of those quieter stretches. We are not in the middle of a dense spiral arm. We are in a relatively calm region, which some astronomers have proposed may be part of why complex life had the opportunity to develop here. Life on Earth required stability, billions of years of it, stability in the Sun's output, stability in Earth's orbit, and perhaps, at the galactic scale, a certain distance from the most violent and energetic regions of the disk. Not too close to the core, where radiation and stellar density are extreme. Not too far from it, where the supply of heavier elements needed for rocky planets and biological chemistry thins out. We sit in what some have called the galactic habitable zone, a rough band of the disk where conditions are, on cosmic standards, relatively gentle. Whether or not that concept holds up under closer scrutiny is something astronomers are still working out, but the idea itself, that our location within the Milky Way might be part of what made our existence possible, adds a new dimension to the question of scale. It is not only that the universe is vast, it is that our position within it, at every level from galactic to stellar to planetary, seems to place us in a particular kind of pocket, not at the edge of everything and not at the centre of everything, but somewhere in the generous middle, close enough to richness to benefit from it, and far enough from extremes to survive them. That's a thought worth sitting with. We are not randomly placed. The physics of our galaxy, the orbital mechanics of our solar system, the chemistry of our planet, all of it fits together in a way that made tonight possible. Made you possible, and this question possible, and the quiet willingness to lie back and think about the stars above you. So now we have a sense of the Milky Way, its shape, its size, its structure, its deep history. It is roughly 100,000 light-years across. It contains somewhere between 200 billion and 400 billion stars. It is wrapped in a halo of dark matter that extends far beyond its visible disk. It has a supermassive black hole at its centre, and spiral arms that drift with the orbiting stars like slow, graceful currents. It is by any standard you care to apply enormous, and yet, the closest thing to us in the universe, the nearest large galaxy to our own, is the Andromeda Galaxy, sitting at a distance of about 2.5 million light-years. On the scale where the Milky Way is a dinner plate, Andromeda is another dinner plate sitting roughly a metre away. The two galaxies are neighbours, in galactic terms. They are in fact gravitationally bound to one another. They are being drawn together slowly across the void, and in about 4.5 billion years they will collide and eventually merge into a new, larger galaxy. Astronomers have already modelled what that collision will look like. An extraordinary slow-motion dance of stars and gas that will play out over hundreds of millions of years, transforming two distinct spirals into something larger and more elliptical, a new structure born from the joining of two. But that collision, dramatic as it sounds, won't destroy individual stars. The distances between stars within a galaxy are so vast, even within the relatively dense disk, that two galaxies can pass through each other without a single stellar collision. The stars will simply drift past each other, pulled into new orbits by the changed gravitational landscape, the way two crowds of people could theoretically walk through each other in a very large space without anyone touching. The merger is a gravitational event, not a physical impact in the way we tend to imagine it. The Milky Way and Andromeda, along with roughly 50 smaller companion galaxies, form what astronomers call the local group. This is our immediate galactic neighbourhood, a cluster of galaxies loosely bound by their mutual gravity, spread across a region about 10 million light-years across. 10 million light-years. That is 100 Milky Ways laid end to end, and the local group is itself a relatively small cluster in the larger context of what surrounds us. Beyond the local group, the next major structure is the Virgo cluster, a massive concentration of more than 1,000 galaxies centered roughly 50 million light-years away. The Virgo cluster exerts a gravitational influence on our local group, a subtle tug that astronomers can measure in the motion of the galaxies within it, a slow drift in the direction of the cluster's enormous concentration of the mass. And the Virgo cluster, vast as it is merely one part of something larger still. In 2014, a team of astronomers published a paper in the journal Nature that quietly reshaped our understanding of where exactly we are in the universe, using a new method to map the motion of galaxies, not just where they are, but where they are heading and how fast. The team, led by astronomer R. Brent Tully of the University of Hawaii, identified a superstructure of galaxies so large that it had simply never been recognized as a coherent entity before. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea encompasses the Milky Way, the local group, the Virgo cluster, and roughly 100,000 other galaxies, all of them flowing slowly in the same general direction, within a structure stretching about 500 million light-years across. 500 million light-years. To put that alongside what we've already discussed, the Milky Way is about 100,000 light-years wide. Laniakea is 5,000 Milky Ways wide. If you could look down on Laniakea from outside it, the entire Milky Way, with all its billions of stars, all its spiral arms, its supermassive black hole, all of us, would be a single, barely distinguishable point of light among 100,000 such points. Laniakea has a centre of gravitational attraction called the Great Attractor, a region toward which all the galaxies within the supercluster are flowing, pulled by a concentration of mass so enormous that it influences the movement of matter across hundreds of millions of light-years. The Great Attractor itself is partially hidden from our view by the disk of the Milky Way, which blocks the light from that region of the sky in optical wavelengths. For decades, astronomers knew something was there, because they could see the effect of its gravity on the motion of surrounding galaxies, but they couldn't see it directly. Only through radio and infrared observations, which can penetrate the galactic dust, have they begun to map what lies there, a vast concentration of galaxy clusters pressed together by their mutual gravity into one of the densest regions of the local universe. And there is a fascinating wrinkle to the story of Laniakea. While it is a real feature of the universe, the galaxies within it really are moving in a coherent pattern, really are flowing toward that shared gravitational centre. It is not, in a strict physical sense, a bound structure. Dark energy, the mysterious force that is causing the universe's expansion to accelerate, will eventually overcome the gravitational attraction that holds the looser parts of Laniakea together. Over vast timescales, the outer regions of the supercluster will drift apart, carried away from each other faster than gravity can pull them back. Laniakea is, in a sense, a temporary structure, a passing arrangement of galaxies that will slowly dissolve as the universe continues to grow. The local group, by contrast, is gravitationally bound. The Milky Way, Andromeda, and the roughly 50 smaller galaxies that travel with them are locked together in an arrangement that will persist. They will not drift apart. Eventually, over billions of years, they will merge, but the larger supercluster around them will slowly come apart, leaving the merged local group increasingly isolated in an expanding cosmos. This is a kind of quiet poetry if you let it be. The universe is both gathering and dispersing, both pulling things together and pushing them apart, both building structure and eventually unraveling it. It is not a static picture. It is a dynamic, evolving story that has been unfolding for nearly 14 billion years and has no clear ending in sight. From here, the story becomes less about measuring the next distance in a chain of comparisons and more about slowly absorbing what these layers of scale suggest when you consider them all at once. We have moved from the solar system to the Milky Way to the local group to Laniakea. Each step has been a multiplication of size by a factor that exceeds easy imagination. And we are not done yet, because Laniakea is not the universe. It is a part of the universe, a neighbourhood in a city that has no visible edge. Take a breath here. Let that thought rest for a moment. There is no need to rush through what comes next. The rest of the journey is about observation as much as measurement, about the feeling of scale as much as the numbers. We are going to keep moving outward together, but from here, we can move a little more slowly. One of the most beautiful discoveries in modern cosmology is that the universe, at its largest scales, is not a featureless expanse. It is not a uniform distribution of matter scattered evenly through space. It has structure. Intricate, sweeping, almost organic-looking structure that astronomers have taken to calling the cosmic web. The cosmic web consists of vast filaments, long threads of galaxy clusters and dark matter stretching across hundreds of millions of light years, with enormous empty voids between them. The filaments connect at nodes where multiple threads meet, forming massive concentrations of galaxies and galaxy clusters. These nodes are the brightest, densest, most energetically active regions of the observable universe, places where thousands of galaxies are pressed together by their mutual gravity, where the intergalactic medium glows hot with X-rays from the compressed gas, where black holes in the centres of large galaxies are actively feeding and releasing jets of energy that can span millions of light years. And between these filaments, between these rivers of matter and light, are the voids. Vast, dark, largely empty regions of space that can span hundreds of millions of light years. Not perfectly empty. Even in the deepest voids there are a few stray galaxies, but so much less dense than the surrounding filaments that they give the cosmic web its defining quality. That contrast between the rich threads of matter and the dark, cavernous emptiness between them. If you were able to see the cosmic web from outside, and no one has or could since we are embedded within it, it would look, scientists often say, like a three-dimensional sponge or a neural network, or like the structure of a soap foam, where the bubbles are the voids and the walls between them are the filaments. It bears a remarkable visual resemblance to the structure of the human brain on a very small scale, the same branching, interconnected pattern of dense nodes linked by thin threads with open space between them. Whether this similarity is meaningful or merely a coincidence of the mathematics of network formation is a question that philosophers and scientists occasionally enjoy debating. What we do know is that the cosmic web is real, and it is the largest coherent pattern ever mapped by human observation. Surveys of the sky, massive projects that have catalogued the positions of millions of galaxies and mapped their three-dimensional arrangement using their redshift, the way their light is stretched by the universe's expansion, have revealed this web in astonishing detail. Projects like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey transformed our picture of the universe from a scattered collection of individual objects into a vast interlocking architecture of filaments and voids that extends as far as our instruments can see. Within this web, Laniakea is a single node, a moderately large supercluster in one region of one filament, in one part of an observable universe that contains millions of similar structures. Neighbouring superclusters have names that most people have never heard. The Shapley concentration, which is the largest nearby concentration of mass, and may actually be exerting a gravitational influence on Laniakea itself. The Perseus-Pisces supercluster, a long chain of galaxy clusters visible in the sky toward the constellations of Perseus and Pisces. The Coma supercluster, centred on the Coma cluster, one of the densest concentrations of galaxies known. Each of these structures is itself enormous. Each contains thousands or tens of thousands of galaxies. Each is a world of complexity and detail that astronomers have spent careers studying. and each of them is just one feature in the web, the way a single city might be one feature on a continent, the way a single mountain range might be one detail on a planet. We are somewhere in all of this, precisely located in a physical sense, though the sense of that location takes some quiet sitting with before it settles into anything resembling comprehension. There is a boundary to what we can see, not because space ends there, it almost certainly doesn't, but because light takes time to travel, and the universe has only existed for a finite amount of time. The oldest light that could possibly reach us set out at the very beginning of the universe, when matter first became transparent enough for photons to travel freely. That happened about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral atoms. Before that moment, the universe was a hot, dense plasma through which light could not travel. After that moment, the universe became suddenly transparent, and the light that was released at that transition, the cosmic microwave background, has been travelling ever since, expanding and cooling along with the universe, arriving at our instruments today as faint microwave radiation from every direction in the sky. The distance to that wall of ancient light, the edge of the observable universe, is about 46 billion light-years in every direction, which gives the observable universe a diameter of roughly 93 billion light-years. You might wonder, if the universe is only 13.8 billion years old, how can light from 46 billion light-years away have reached us? The answer lies in the expansion of the universe itself. The space between us and those distant regions has been expanding since the Big Bang, so the light that left them long ago has been travelling through an expanding medium, and the sources of that light have since moved much further away. The light we receive from the edge of the observable universe was emitted when those regions were much closer to us than they are now. This is one of the more counterintuitive aspects of cosmology, and it's worth sitting with gently rather than trying to force it into familiar patterns. The universe does not behave like a room with walls. It behaves more like a surface that is continually expanding. Think of dots drawn on a balloon being inflated, each dot moving away from every other, with the space between them growing even as the dots themselves move. The expansion is not of matter through space, it is of space itself. And that expansion, combined with the finite age of the universe and the finite speed of light, produces the observable universe, the sphere of space from which any information could in principle have reached us by now. Beyond that sphere there is almost certainly more, likely much more, possibly infinitely more, but we cannot observe it. We cannot receive any signal from it. It exists beyond our horizon in a way that is, for practical purposes, absolute. The regions beyond the observable universe are not inaccessible because of some physical barrier, but because light from there has never had time to reach us, and at the current rate of expansion, it never will. The universe is expanding faster than light can cross some of those distances, which means that some regions of space are, in the most literal sense, permanently beyond our knowledge. There is something both humbling and oddly peaceful about that. The universe is larger than we can ever measure. It is larger, in principle, than any observation could fully encompass, and yet we sit here, inside this incomprehensible vastness, capable of understanding it at least in outline, capable of reasoning about its structure and history, capable of knowing that we cannot know its full extent. That combination, the knowledge of the limit and the knowledge of what lies just within it, is one of the quieter gifts of cosmology. For our purposes tonight, the observable universe is a sphere about 93 billion light-years across, containing roughly 2 trillion galaxies, each of which contains hundreds of billions of stars, each of which may have planets, and some of which, statistically almost certainly, have conditions capable of supporting some form of life. The number of stars in the observable universe exceeds the estimated number of grains of sand on all of Earth's beaches. The number of possible planets exceeds that again. We are, in terms of sheer occurrence, among the most common kinds of structures in the cosmos. There are likely more planets like Earth, or at least roughly similar to Earth, than any number you have personally encountered in your life would help you visualize. And yet each one of those worlds is separated from all the others by distances so vast that the stars between them offer no easy passage. The universe is full and lonely at the same time, abundant in material and sparse in connections. Every galaxy is a city of stars, and the space between galaxies is a desert of such extraordinary scale that the cities might as well not know of each other's existence. We are surrounded by company we cannot visit and cannot hear. Here is something that often surprises people when they first hear it. The universe is not sitting still. It is not a fixed container that space and galaxies inhabit. The universe itself is expanding. Every galaxy beyond our local group is moving away from us, not because galaxies are drifting through space like ships across an ocean, but because the space between them is stretching, growing, adding new distance between every point simultaneously. This was first worked out in the late 1920s, when Edwin Hubble, the same astronomer who established that other galaxies existed beyond the Milky Way, discovered that nearly all distant galaxies appeared to be receding from us, and that the farther away they were, the faster they seemed to be receding. The relationship between distance and recession speed became known as Hubble's law, and the constant that describes it, the Hubble constant, has been the subject of precise measurement and occasional disagreement ever since. The consequence of an expanding universe is profound and strange. It means that in the far future, the universe will look very different from the way it looks tonight. The most distant galaxies we can currently observe will, over billions of years, recede beyond our observable horizon, their light redshifted into invisibility, their signals too stretched to carry any meaningful information. A civilization living 100 billion years from now, in whatever form intelligence might take by then, would look out at a universe that appeared to contain only its own local group. All the other galaxies, all the filaments of the cosmic web, all the superclusters and voids and walls of galaxies that we can map today would be gone from view, vanished not by destruction but by distance, pushed beyond the observable horizon by the relentless expansion of space. That future civilization, had they no record of our observations today, would look at the sky and conclude, as astronomers once concluded, that their galaxy was the universe. They would have no evidence of anything beyond. The cosmic web, the 2 trillion other galaxies, the beautiful intricate architecture of the observable universe, all of it would be invisible, irretrievably beyond any possible observation. In that sense, we live at a remarkably fortunate moment in cosmic history. The universe is old enough that galaxies have had time to form and develop, stars have had time to forge the heavy elements that make chemistry and biology possible, and planets have had time to cool and stabilize into the conditions that allow complex life. And yet it's not so old that the expansion has carried the other galaxies beyond our sight. We can still see them. We can still map them. We can still piece together the picture of the cosmic web and the observable universe in something like its full extent. We are witnesses to the universe at a very particular moment in its history, and we may be among the last inhabitants of the cosmos who have the ability to observe it at something close to its maximum visible extent. That is a thought that carries a particular kind of weight when you hold it in the quiet of an evening. Not a frightening weight, a meaningful one. Let's return for a little while to something closer, because in all of this talk of billions of light years and trillions of galaxies, it is easy to lose the texture of the scale, the actual physical sense of how much empty space there is, even within the structures that seem to be full of matter. Consider the Milky Way. It contains, as we've established, somewhere between 200 and 400 billion stars. That is an extraordinary number of suns, and yet the Milky Way's disk is roughly 100,000 light-years across and 1,000 light-years thick, an enormous volume of space. When you divide the number of stars by the volume of the galaxy, you find something perhaps surprising. Most of the galaxy is empty. Vastly, almost perfectly empty. The stars are scattered through the disk the way a few dozen fireflies might be scattered through an area the size of a small country. Each star is an island of light in an ocean of dark space that extends in every direction for light years. The nearest star to our Sun, Proxima Centauri, is about 4¼ light years away. At the scale where the Sun is the size of a grapefruit, roughly 12 centimetres across, Proxima Centauri would be another grapefruit sitting roughly 3,400 kilometres away. If the Sun were in London, the nearest star would be somewhere past the Urals, past the Caspian Sea, past Central Asia. 2 grapefruits separated by the width of a continent with nothing in between. That is the density of our cosmic neighbourhood. Scale that up to the whole galaxy, and you begin to appreciate just how much of the Milky Way is not stars. It is interstellar space, vast, cold, dark, and very nearly empty, threaded with diffuse clouds of gas and dust that glow faintly in radio frequencies, and otherwise as vacant as any void. The galaxy is, in a very physical sense, mostly nothing. Its stars are extraordinarily numerous and yet extraordinarily sparse. If you were somehow dropped at a random point within the Milky Way's disk, the probability of landing within any particular solar system would be vanishingly small. You would almost certainly find yourself in the middle of interstellar space, with no nearby star visible as more than a point of light in an otherwise empty sky. This emptiness is not unusual. It is the normal condition of the universe. Matter, ordinary matter, the kind that makes up stars and planets and you, accounts for only about 5% of the universe's total energy content. The rest is dark matter and dark energy, both invisible in different ways, both mysterious, both essential to the structure of everything we observe. The universe is, in its deepest nature, mostly things we cannot directly detect, shaped by forces we do not fully understand, structured in ways that become visible to us only through their effects on the small fraction of matter that glows. And yet here we are inside it having this conversation. 2 trillion. That is the current best estimate for the number of galaxies in the observable universe. The number was revised upward significantly in 2016 when a study led by Christopher Consolis at the University of Nottingham analysed data from the Hubble Space Telescope and concluded that previous estimates had missed a large fraction of small, faint galaxies, particularly in the early universe, when smaller proto-galaxies were far more numerous. The true number of galaxies in the observable universe that study concluded was at least 10 times higher than previously thought. 2 trillion galaxies, each one a collection of hundreds of billions of stars, each one separated from its neighbours by distances that dwarf even its own enormous size. When you look at a photograph taken by the Hubble Space Telescope in a region of sky that appears, to the naked eye, as empty black space, the famous Hubble Deep Field photographs, taken by pointing the telescope at a tiny, apparently blank patch of sky for days at a time, nearly every smudge of light in the image is not a star. It is an entire galaxy, thousands of galaxies visible in a region of sky smaller than the width of a grain of sand held at arm's length. The universe is not sparse in galaxies, it is saturated with them, and yet the space between them is so vast that the universe can be, at the same time, almost entirely empty. These two facts coexist without contradiction. Abundance and void, structure and emptiness. 1 trillion candles spread across a room so large that each candle illuminates only its own small corner, and the space between them remains even so immeasurably dark. When you think about what it means for the Milky Way to be one among 2 trillion galaxies, a natural response might be to feel diminished. To feel that the Milky Way, and by extension our solar system, and by extension our planet, and by extension you, are so cosmically insignificant as to be effectively non-existent. That response is understandable. But it is not perhaps the most useful way of sitting with this information. Here is another way of looking at it. The Milky Way is not an afterthought. It is not a random accident. It is a fully realized, complex, ancient, self-organizing system that has been building its structure and evolving its populations of stars for more than 13 billion years. It contains within it the only example of self-aware life that we know of in the entire universe. Whether other examples exist elsewhere, and the mathematics of probability strongly suggest they might, we have not found them. We have found us, here, inside this particular galaxy, orbiting this particular star, on this particular planet on this particular evening, asking this particular question. That is not nothing. That is in fact one of the most remarkable configurations of matter and energy ever produced by the universe as far as we currently know. The universe is large enough to make a Milky Way seem small, but the Milky Way is complex enough to make a galaxy seem like a remarkable achievement, and you are complex enough to make the whole comparison meaningful. We have mentioned dark matter and dark energy several times in passing, the way you might mention load-bearing walls when describing a house, acknowledging their importance without stopping to explain in detail why they are there. But these two phenomena are so fundamental to the structure of the universe, we have been exploring that they deserve a little more time before the night grows quieter. Dark matter, as we have touched on, is a form of mass that does not interact with light. It neither emits nor absorbs electromagnetic radiation of any kind, which means no telescope, optical, radio, infrared, X-ray or otherwise, can see it directly. What astronomers can do is measure its effects. In the 1970s, astronomer Vera Rubin and her colleague W. Kent Ford made careful measurements of the rotation of spiral galaxies and found something unexpected. The stars in the outer regions of galaxies were moving too fast. By Newton's laws of gravity, the stars at the edges of a galaxy should be moving more slowly than the stars closer to the centre, the way the outer planets of our solar system move more slowly than the inner ones. But galaxy after galaxy showed the same strange pattern. The rotation curve was flat. Stars at the edges moved at nearly the same speed as stars near the centre. The only explanation that fit the observations was that galaxies contain far more mass than their visible stars, and gas could account for. Mass distributed in an extended spherical halo that surrounds the visible disk and provides the additional gravitational pull needed to hold the outer stars in their fast-moving orbits. That invisible mass, whatever it is made of, is dark matter. Decades of searching have not identified a specific particle responsible for dark matter. Detectors buried deep underground, satellite observations of the cosmic microwave background, analyses of galaxy clusters, gravitational lensing studies, all of these have confirmed that dark matter exists and provided increasingly detailed maps of its distribution without revealing its fundamental nature. It is one of the most significant open questions in physics. Something that makes up approximately 27% of the universe's total energy content is behaving in a way we cannot currently explain from first principles. Dark energy is even stranger. It is the name given to whatever is causing the expansion of the universe to accelerate. When astronomers discovered in the 1990s that distant supernovae were dimmer than expected, indicating they were further away than a uniformly expanding universe would predict, the conclusion was unavoidable. The expansion was not slowing down over time, as gravity pulling matter together would cause it to do. It was speeding up. Something was pushing the fabric of space apart with increasing force over time. That something, now called dark energy, constitutes roughly 68% of the universe's total energy content. It is the dominant component, and we have no physical theory that fully accounts for it. Think about that for a moment. The universe is composed roughly of 5% ordinary matter, stars, planets, gas, dust, you, 27% dark matter, and 68% dark energy. The part of the universe that we can see, that we understand, that we can model and study and describe is 5%. The rest is, in the most literal sense, beyond our current understanding. The universe we have been discussing tonight, the Milky Way, the cosmic web, the 2 trillion galaxies, the entire observable cosmos in all its extraordinary scale and complexity, is a kind of surface decoration on something whose deeper nature remains unknown. This is not a discouraging thought, though it might initially seem that way. It is, more than anything else, a reminder that the universe has not finished surprising us. The discovery of dark matter and dark energy did not close the book on cosmology. It opened a set of chapters that have not yet been written, pointing to physics beyond our current best theories, to phenomena that have existed since the beginning of the universe, and that we are only beginning to recognize as distinct and fundamental parts of the cosmic picture. The universe we have been exploring tonight, with all its galaxies and filaments and superclusters and voids, did not always look this way. It has a history, and that history is one of transformation from extraordinary simplicity to extraordinary complexity. Approximately 13.8 billion years ago, the universe began in a state of conditions so extreme that no everyday analogy does them justice. Temperature, density, energy, all of these quantities were at values that make even the interior of a star seem mild. In the first fractions of a second, the universe was a sea of particles and radiation so tightly packed and energetically interacting that the concepts of space and time themselves were defined differently than they are today. As the universe expanded, it cooled. Within the first few minutes, protons and neutrons were combining to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium. This process is called Big Bang nucleosynthesis, and its predicted proportions match exactly what we observe in the oldest, most chemically pristine regions of the universe today. That match is one of the strongest pieces of evidence that the standard model of cosmology, the model that describes the Big Bang and the subsequent expansion, is correct. Over the next several 100,000 years, the universe continued cooling until the temperature dropped enough for electrons to combine with nuclei into stable neutral atoms. This was the moment we referred to earlier, the moment when the universe became transparent and the cosmic microwave background was released. Before this moment, photons were constantly interacting with the charged particles around them, unable to travel freely. After it, light was free to move across the universe for the first time. The universe lit up. Or rather, it became the kind of place where light could exist meaningfully, and then proceeded to cool and dim as the expansion continued. What followed was a period astronomers call the Cosmic Dark Ages, a span of hundreds of millions of years during which the universe was filled with hydrogen and helium gas, but no stars, no light sources, no galaxies. Just an expanding, cooling, dark expanse of gas, slowly developing the subtle density variations that would eventually, under gravity's patient encouragement, collapse into the first stars. The first stars were very different from the stars we know today. They formed from pure hydrogen and helium, with no heavier elements at all, no carbon, no oxygen, no iron, no calcium. They were extraordinarily massive and correspondingly short-lived, burning hot and bright for only a few million years before exploding as supernovae or collapsing directly into black holes. And in those explosions, something crucial happened. Heavier elements were created for the first time. Carbon, oxygen, nitrogen, silicon, iron, all of the elements that make planets and chemistry and biology possible, were forged in the nuclear furnaces of those first stars and scattered into the surrounding gas by their deaths. The universe grew chemically richer with each generation of stars. Subsequent stars formed from gas clouds that included the debris of previous stellar generations, making them richer in heavy elements, longer lived, more capable of forming the kind of planetary systems where complex chemistry can develop over geological timescales. Our Sun is a third-generation star formed about 4.5 billion years ago from a cloud of gas and dust that was already enriched with the products of previous stellar generations. The heavy elements in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, were made in stars that died long before our solar system was born. You are, quite literally, made of stellar material. The atoms in your body have been part of stars. They have travelled through the interstellar medium. They have been part of gas clouds and planetary surfaces and oceans and the cells of other organisms across billions of years of cosmic time. The universe is not separate from you, watching you from a distance. You are made of it. Your body is a temporary arrangement of matter that has existed in many other forms across cosmic history, and will exist in many other forms after this arrangement ends. That is a thought that, if you let it settle slowly, has a particular kind of softening effect on the ordinary anxieties of a day. There is a reason that the kind of exploration we have been doing tonight tends to have a calming effect rather than an alarming one, even though the scale of what we have been discussing is genuinely beyond ordinary comprehension. Something about the immensity of the universe, properly absorbed, gently encountered, not rushed through, seems to quiet the part of the mind that generates worry. Philosophers and scientists have offered various explanations for this. Some suggest that the vastness of the universe puts our personal concerns into perspective, not by making them meaningless, but by placing them inside a frame so much larger that the frame itself becomes a kind of comfort. Your worries, your uncertainties, your unresolved questions about how things will turn out, all of them are real, and all of them matter deeply, but they are happening inside a universe of such extraordinary richness and complexity that there is, literally, space for all of them. There is room, in the cosmic accounting, for difficulty and beauty to coexist without contradiction. Others have noted that there is something inherently restful about thinking at scales that exceed our capacity for anxiety. Anxiety, as a psychological phenomenon, tends to be very local. It is concerned with the near future, the immediate environment, the people and circumstances that are closest to us. When the mind shifts to scales of billions of light years and billions of years, the machinery of anxiety doesn't quite know what to do. It has nothing to latch onto, and in that brief suspension of its usual operation, there can be a kind of relief. Still, others have pointed out that the universe's indifference to human concerns is not the same as hostility. The universe is not ignoring you. It simply operates at a scale and time frame in which individual human events are not the central narrative. And recognizing that, really feeling it, not just thinking it as an abstraction, can be liberating. You're not responsible for the universe's trajectory. You're not required to solve its mysteries or manage its evolution. You're simply asked to be here, in this moment, as one expression of what happens when matter and energy organize themselves with sufficient complexity over sufficient time. One of the more quietly astonishing facts about our cosmic neighbourhood is that the entire local group, the Milky Way, Andromeda, and the roughly 50 smaller galaxies that travel with them, is in motion. Not just orbiting within the Milky Way, not just the solar system moving through the galaxy, but the entire structure of the local group moving through the universe at roughly 600 kilometers per second in the direction of a concentration of mass known as the Great Attractor. 600 kilometers per second. That is 60 times the speed needed to escape Earth's gravity. It is fast enough to travel from here to the moon in about 10 minutes, and yet at the scale of the universe, it is a gentle drift, a slow lean in the direction of gravitational influence, the same way a ball rolls softly toward the bottom of a shallow bowl. The Great Attractor is not fully understood. It lies in a region of the sky that is particularly difficult to observe because it is behind the plane of the Milky Way's disk, where dust and gas obscure our view in optical light. Radio and X-ray observations have revealed that it corresponds to a large concentration of galaxy clusters, a place where the cosmic web's filaments converge into a particularly dense node of matter. Recent surveys suggest that this region may itself be part of a larger basin of gravitational attraction, associated with the Shapley concentration, one of the most massive structures in our cosmic neighbourhood, lying several hundred million light-years away. What this means, in the most concrete terms, is that our entire supercluster, Laniakea, with its 100,000 galaxies, is slowly being drawn towards something even larger. Not rushing, not in any kind of cosmic emergency, just drifting, the way objects always drift toward the things that pull them, at rates that seem fast in absolute terms but are insignificant on the timescales over which the universe unfolds. This is the rhythm of the cosmos: slow accumulation, gentle drift, long pauses between dramatic events. The universe builds its structures over hundreds of millions of years. It collapses gas clouds into stars over millions of years. It merges galaxies over billions of years. It will expand for billions of years more before any significant change in its large-scale structure becomes apparent. On the timescales of human life and human history, the universe is essentially still. The stars seem fixed. The galaxies seem stationary. The cosmic web seems like a photograph rather than a living process. But over the deep time of the universe, everything is moving. Everything is slowly arranging and rearranging itself, pulled by gravity, pushed by dark energy, building structure in some places and dissolving it in others. The universe is an ongoing process, not a finished product, and we happen to be present during a particular moment in that process. A moment when complexity has reached the point of self-awareness, when matter has organised itself into systems capable of looking back at the whole and wondering what it means. That is where we find ourselves tonight. There is an exercise that astronomers sometimes suggest to people who want to get a sense of the scale of the universe. Hold your thumb up against the night sky, blocking a small patch of stars. The patch covered by your thumb, in a clear dark sky, might obscure a handful of visible stars. Now consider that the Hubble Space Telescope, pointed at a patch of sky smaller than the area covered by your thumbnail at arm's length, and left exposed for days, revealed thousands of galaxies. Each galaxy contains hundreds of billions of stars. That single thumbnail's worth of sky, apparently empty to the naked eye, contains more stars than have ever been given names. There are more stars in the observable universe than grains of sand on all of Earth's beaches. That comparison has become a familiar one, almost a cliché of popular science, but it bears repeating because no matter how many times you hear it, it takes a long moment to land with any real force. Every grain of sand, every single grain, on every beach, on every continent, at the bottom of every ocean, corresponds to at least one star in the observable universe. Probably more than one. The number of stars in the observable universe is approximately 10 to the power of 24. That is a 1 followed by 24 zeros. And yet, for all of this abundance, every star is unique. Each one has a different mass, a different temperature, a different lifetime, a different history. Each one that we can observe closely enough to study has planets, or the remnants of a planetary system, or at minimum a disk of material that was once in the process of becoming planets. Each one that is old enough has seeded the space around it with heavy elements through its winds and its eventual death. Each one is, in the full sense of the word, a world, a centre of activity and energy and chemistry, radiating into the surrounding space, influencing the region around it, marking out a small territory of warmth and light in the vast cold of interstellar space. Our Sun is one of these, not distinguished in any obvious way from the great population of stars in the Milky Way, not especially massive, not especially luminous, not located in any particularly notable region of the galaxy. It is a G-type main sequence star, a category so common that it comprises a substantial fraction of the stars in the Milky Way. There may be billions of stars in our galaxy alone that are similar to the Sun in size, temperature and age, and yet our Sun is the one that warms the Earth, that drives the water cycle, that provides the energy that powers nearly every living thing on this planet. It is ordinary in its type and extraordinary in its consequence, which is true, in different ways, of a great many things. We have mentioned Andromeda several times tonight, the large spiral galaxy sitting about 2.5 million light-years away, the nearest major galactic neighbour to the Milky Way. But the relationship between our galaxy and Andromeda is not merely that of distant neighbours. It is the relationship of two objects on a slow, inevitable trajectory toward each other. The Milky Way and Andromeda are falling toward each other. Their combined gravity is drawing them together across the void, and while the precise details of the eventual collision have been a subject of ongoing refinement as astronomers gather better data on the galaxy's velocities, the broad picture is clear. In roughly 4 to 5 billion years, the two galaxies will begin to interact, their outer regions touching and distorting, their spiral structures gradually disrupted and transformed. Over the subsequent billions of years, the two galaxies will pass through each other, drawn back by gravity for a second interaction, and eventually settle into a merged structure, a larger, more elliptical galaxy, sometimes fancifully referred to in advance as Milkomeda or Milkdromeda. Our Sun, and whatever remains of our solar system at that point, will likely be swept into a different region of the merged galaxy, its orbit transformed by the gravitational upheaval of the merger. But as we discussed earlier, the probability of any actual collision between individual stars is extraordinarily small. Stars are too far apart for galaxy mergers to be physically violent at the stellar level. What changes are orbits, not positions in any direct way. The night sky, by that point in the far future, would look extraordinary. As the galaxies approach, Andromeda would grow larger and larger in the sky, eventually spanning an arc larger than the current Milky Way band, a second disk of stars cutting across the heavens in addition to our own. During the merger, the sky would be filled with double the stars, massive regions of star formation blazing with young, hot blue stars, the Milky Way's familiar band distorted and bent into new shapes by the gravitational interplay. None of us will see it. The relevant timescales are so far beyond the span of any human civilization that the exercise is purely imaginative. But there is something quietly wonderful about knowing that the story of our galaxy is not finished, that the Milky Way is moving through a universe that continues to act upon it, and that billions of years from now it will be part of something new, something larger, shaped by the same gravity that holds you to the Earth tonight. The universe does not stand still. It is always in the process of becoming something different from what it was. It is worth pausing to appreciate not just what we know about the universe's scale, but how we came to know it. The story of how humanity extended its sense of the cosmos from the Earth to the solar system, to the Milky Way, to the observable universe, is a story of instruments and ingenuity, of patient observation and mathematical insight, of discoveries made by people who spent their careers staring at data that most of the world never sees. The first step was simply building telescopes powerful enough to resolve individual stars in other galaxies. Edwin Hubble worked with the Hooker telescope at Mount Wilson Observatory in California, at the time the largest telescope in the world, to observe a particular class of pulsating stars called Cepheid variables in the Andromeda Nebula. Cepheid variables have a known relationship between their period of pulsation and their luminosity, which means that by measuring how quickly they pulse, you can calculate how bright they actually are. By comparing that true brightness to how bright they appear in the telescope, you can calculate how far away they must be to appear that faint. Hubble made those measurements in 1923 and 1924, and the distance he calculated, vastly larger than the Milky Way itself, established beyond reasonable doubt that the Andromeda Nebula was an external galaxy. That single observational achievement changed our picture of the universe more dramatically than any discovery since Copernicus moved the Earth out of the centre of the solar system. From there, the development of radio astronomy, infrared astronomy, X-ray astronomy, and eventually space-based telescopes opened the entire electromagnetic spectrum to observation. The Hubble Space Telescope, launched in 1990, gave us our deepest views of the distant universe, revealing those thousands of galaxies in each tiny patch of apparently empty sky. the Planck satellite mapped the cosmic microwave background with extraordinary precision, giving us a detailed snapshot of the universe's earliest observable state. The Gaia mission charted the positions and motions of more than 1 billion stars in the Milky Way. The Event Horizon Telescope imaged the shadows of supermassive black holes, and the James Webb Space Telescope, the largest and most powerful space telescope ever launched, has been observing galaxies in the early universe with a clarity and sensitivity that continues to produce unexpected results. These instruments are not just data collecting machines, they are extensions of human curiosity. They are the result of thousands of researchers, engineers, administrators, and supporters dedicating portions of their lives to the project of understanding where we are. Every image, every spectrum, every catalogue of stars or galaxies is the product of an enormous collective effort, sustained over decades by the simple conviction that it matters to know, and it does matter, not necessarily in a practical day-to-day, immediately applicable way, though the technologies developed in service of astronomy have found countless practical uses. But it matters in the deeper sense that it shapes how we understand ourselves. Every expansion of our map of the universe has changed something in the human picture of who and what we are. Every discovery that the universe is larger, older, stranger, and more structured than previously thought has asked us to revise our story of ourselves in the most fundamental way. And the story has, each time, become richer for the revision. There is a particular satisfaction, hard to describe but real, in the kind of mathematics that describes the universe at its larger scales. It is not the sharp, algorithmic satisfaction of solving a puzzle or balancing an equation. It is something softer and broader. It is the satisfaction of a framework so clear and consistent that the same equations that describe the orbit of the Moon around the Earth also describe the orbit of the Milky Way around the centre of Laniakea, separated by a factor of 100 million in scale. The mathematics scales without breaking. The same gravity that holds the apple to the tree holds the galaxy in its shape. That universality is not something we had any reason to expect in advance. There was no logical requirement that the laws discovered in Earth-based laboratories would apply equally well to the behaviour of matter billions of light-years away. And yet they do. Every observation we have made of distant galaxies, every measurement of light from ancient quasars, every analysis of the cosmic microwave background has been consistent with the same set of physical laws. The universe is, in this sense, comprehensible. Not simple, not easy to understand in detail, but obedient to consistent principles that we can discover and describe. That comprehensibility is one of the deepest mysteries in science. It is also one of its quiet gifts. The universe did not have to be the kind of place where understanding was possible. It could have been chaotic, inconsistent, governed by rules that shifted from place to place and moment to moment. Instead, it turns out to be a place where the same laws apply everywhere and always, where the same mathematics describes the motion of atoms and the motion of galaxies, where patient observation and careful reasoning can actually reveal something true about how things work. Whether that comprehensibility is a fundamental feature of reality, a reflection of how minds necessarily structure experience, or simply a lucky alignment of our cognitive tools with the universe's actual structure, these are questions that shade into philosophy and epistemology rather than physics. But the fact of it, whatever its explanation, is something worth noting tonight. You live in a universe that can, at least in principle, be understood. That is not nothing. That is perhaps one of the most remarkable things about the place. If you've been listening for a while, if the pace has slowed a little since we first set out, if the images have begun to blur slightly at the edges the way they do when the mind starts to move toward rest, that is exactly as it should be. The scale of the universe is not something to be grasped all at once, held firmly in mental focus for 2 hours and then set down. It is something to be circled, approached from different angles, allowed to sink in over time like rain into soil. The numbers we have visited tonight are not destinations, they are signposts. They point towards something that the intellect can acknowledge and the body can begin to feel, even if the mind cannot fully contain it. The sense of being inside something vast. The sense of being included, not as the centre of everything, but as a genuine part of everything. The sense that the space above you is not empty and foreign, but continuous with the place you are, the same space that holds the stars and the galaxies and the cosmic web, all of it connected, all of it the same universe. That sense, when it is genuinely felt rather than merely described, has a quality that is difficult to name but easy to recognize. It is the quality of the mind resting in something larger than itself, of thoughts slowing and simplifying, not from lack of interest but from a kind of absorption. The universe is too large to be held anxiously. It can only be rested in. And resting in it, even for a few minutes, can change something in the quality of a night. People have always sensed this, even before science gave them the numbers. The impulse to lie on their backs in the grass and look up at the stars on clear evenings is as old as human consciousness. The sky has always done something to attention that the ground does not. It opens it. It allows it to spread outward rather than contracting around whatever is nearest and most pressing. The sky is the oldest meditation object we have, and the universe we have described tonight is simply the most complete account we have yet assembled of what that sky actually is. Now the scale is known, or approximately known, within the observable limit, and the knowing enriches the looking. When you look up at the band of the Milky Way on a dark night, you are not looking at a pretty pattern in the sky. You're looking into the disk of a spiral galaxy that is more than 100,000 light-years across and 13 billion years old. When you look at the faint smudge of Andromeda visible on autumn nights without a telescope, you are seeing, with your naked eye, the light that has travelled 2.5 million years to reach you. The light of 250 billion stars arriving in your eye in a beam so faint that most people don't notice it is there at all. When you look at a dark patch of sky between stars and imagine, as the Hubble telescope has shown you, that darkness is filled with galaxies beyond galaxies, each one 100,000 light-years across, each one containing hundreds of billions of stars, each one more ancient and complex than any human civilization. You're practicing a kind of awareness that is unique to this particular moment in the history of a species that has been asking questions for a few 100,000 years and has only recently, in the last century or so, begun to receive answers at this scale. That is something to sit with quietly. Let's come back one more time to our immediate neighbourhood, because in all the talk of superclusters and cosmic webs in the observable universe, there is something grounding about returning to the local group, to the relatively small collection of galaxies that constitutes our gravitational family. The local group is a collection of roughly 50 to 60 known galaxies, spread across an irregular region of space about 10 million light-years in diameter. The two dominant members are by far the Milky Way and Andromeda. Together they contain the great majority of the local group's total stellar mass. Around them orbit a collection of smaller companions, the large and small Magellanic Clouds, visible to the naked eye in the southern hemisphere as detached patches of the Milky Way. The Triangulum Galaxy, a smaller spiral about 3 million light-years away. A scattering of dwarf irregular and dwarf elliptical galaxies with names like Fornax, Sculptor, Carina, Draco, Ursa Minor and Leo. Modest in size, ancient in age, scattered across the local group's volume like small moons around a pair of planets. The Magellanic Clouds deserve particular mention. Visible from the southern hemisphere as two bright patches of light separated from the main band of the Milky Way, they are satellite galaxies, companions that orbit our galaxy the way moons orbit a planet. The large Magellanic Cloud sits about 160,000 light-years away, making it one of the closest galaxies to the Milky Way. It is connected to our galaxy by a bridge of gas and stars called the Magellanic Stream, a trail of material stretched out by the tidal forces of our galaxy's gravity. The Milky Way is, in a real sense, slowly absorbing both Magellanic clouds, pulling material from them, incorporating them into its own growing structure. This cannibalism, if that's not too dramatic a word, is common at the galactic scale. Larger galaxies grow partly by absorbing smaller ones over time. The Milky Way is currently in the process of incorporating several smaller dwarf galaxies, whose stars are being stretched into long streams by the tidal forces of our galaxy's gravity. These stellar streams are visible to astronomers as elongated bands of stars with similar chemical compositions and motions, tracing the paths of the absorbed galaxies as they spiral inward toward eventual integration. The history of the Milky Way is partly a history of mergers and absorptions, small galaxies falling in and being torn apart, contributing their stars and gas to the growing whole. The Milky Way we inhabit today is the result of that long history of assimilation. Some of the oldest stars in our galaxy's halo may have originated in smaller galaxies that were absorbed billions of years ago, before the Milky Way had the disk we know today. The galaxy is, in that sense, a composite, built from the contributions of many smaller systems over the course of its long existence. Understanding this makes the Milky Way feel less like a fixed thing and more like an ongoing process. It is not a static island in the universe. It is a dynamic, evolving system that has been gathering material and changing its structure since the universe was young. In 4.5 billion years, when it merges with Andromeda, that process will continue, the two galaxies becoming one, each contributing its stars and gas and history to the new whole. There is something gentle in that image. Things come together over time. Nothing is permanent in its current form, but what exists is the result of everything that came before it. The Milky Way carries within it the memory of every galaxy it has absorbed, every cloud of gas it has condensed into stars, every stellar generation that has lived and died and enriched the interstellar medium with its elements. It is a library as much as a galaxy, a record of what came before, encoded in the motions and compositions of its stars. We have been moving comfortably through the universe at large scales for a while now, and it feels like the right moment to briefly revisit something we mentioned earlier, the cosmic microwave background, because it is one of those pieces of evidence that, once you understand what it actually is, permanently changes how you feel when you consider the night sky. The cosmic microwave background is the oldest light in the universe. It is the photons that were released when the universe was about 380,000 years old. A blink in cosmological time, but still an unimaginable span by human standards. Before that release, the universe was so hot and dense that it was opaque. Photons were constantly colliding with free electrons and protons, unable to travel any meaningful distance before being scattered. The universe at that stage was filled with a dense, glowing plasma, similar in some ways to the interior of a star. When the temperature dropped enough for electrons to combine with nuclei into neutral hydrogen atoms, the plasma became transparent. The photons, suddenly free to travel, flooded outward into the expanding universe. That flood of light, the last light emitted by the hot plasma, has been travelling ever since. It has been travelling for nearly 14 billion years, and during that entire journey, the universe has been expanding, stretching the wavelength of that light from the visible or near-infrared range it was originally emitted into the microwave range it occupies today. It has been cooled by expansion from a few thousand degrees to about 2.7 degrees above absolute zero. Today, that ancient light fills the entire observable universe equally in every direction. It is, effectively, the background of the sky, always there, in every direction, in every observation, behind every star and galaxy and supercluster. When a radio antenna or microwave telescope is pointed at the sky, it picks up this ancient glow, this fingerprint of the early universe, this record of what the cosmos was like when it was 13,000 times younger than it is now. The pattern of the cosmic microwave background is not perfectly uniform. It has tiny variations, fluctuations of 1 part in 100,000 in temperature across different regions of the sky. Those tiny variations are the seeds of everything that followed. They are the initial density fluctuations that, under gravity's influence over billions of years, grew into the structures we have been exploring tonight. The galaxies, the clusters, the superclusters, the cosmic web. The entire large-scale architecture of the observable universe grew from those tiny wrinkles in the ancient light. Astronomers have mapped those fluctuations in extraordinary detail. First with the COBE satellite in the early 1990s, then with WMAP, and most recently with the Planck satellite, which produced the most detailed map yet of the cosmic microwave background in 2013. From those maps, they've been able to extract an enormous amount of information about the universe's composition, age, geometry, and history. The measurements from Planck, combined with other observations, give us a universe that is 13.8 billion years old, geometrically flat within current measurement precision, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, and began with an early period of extraordinarily rapid expansion called inflation. All of that information, the composition of the cosmos, the age of the universe, the seeds of every galaxy, is encoded in the pattern of temperature variations in a faint microwave glow that fills the sky. That faint glow is the oldest observable thing in the universe. It is the echo of the Big Bang, still audible if you have the instruments to listen. The universe has been trying to tell us its history all along. We have simply been learning, slowly and with remarkable persistence, how to read it. We have covered a great deal of distance tonight, from the Earth to the solar system, from the solar system to the Milky Way, from the Milky Way to the local group, from the local group to Laniakea, from Laniakea to the cosmic web, from the cosmic web to the observable universe and its ancient glowing edge. We have visited supermassive black holes and dark matter halos and the first stars and the cosmic microwave background. We have imagined what the sky will look like in 4 billion years when Andromeda fills the heavens, and what it was like in the first few minutes of the universe when there were no stars at all. If you are still with us, if you have carried these images through the hours we have been walking together, then something has been building quietly in the background of all these descriptions. Not an anxiety, not an intellectual weight, something lighter than that. The particular quality of mind that comes from sitting with immensity long enough that it stops being alarming and starts being companionable. The universe is large. It is incomprehensibly, measurelessly large. Our galaxy is one among 2 trillion others in the observable portion alone. Our sun is one among hundreds of billions of stars in the Milky Way. Our planet is one of a likely trillion scattered through the galaxy. And you are one person on one planet in one solar system, in one spiral arm of one galaxy, among 2 trillion. And yet, you are the part of the universe that is awake tonight. You are the arrangement of matter that, at this particular moment, is doing the extraordinary thing of asking what the universe is. Not just existing in it. Everything exists in it. But examining it, holding it in attention, wondering about its size and shape and history and meaning. The universe produced you, and you are looking back at it with curiosity and wonder, and that exchange is something the rest of the cosmos cannot do. The stars cannot wonder about you. The galaxies cannot consider their own size. The cosmic web has no awareness of itself. Only here, in this improbable arrangement of atoms on a small planet in the outer reach of a spiral galaxy, does the universe seem to have found a way of considering itself. And that, for all the vastness we have described, is one of the most remarkable facts we have encountered tonight. You're not lost in the universe, you're a feature of it. People used to get lost. Before maps, before compasses, before GPS, the experience of not knowing where you were relative to everything else was a source of genuine anxiety. The development of navigation, the ability to orient yourself in space using stars, landmarks, or instruments, was one of the great practical gifts of science to human life. Knowing where you are changes the feeling of being in a place. The same forest feels different when you know which direction is north. The same ocean feels different when you know where the shore is. We have, in the course of this evening, been doing something similar at a much larger scale. We have been establishing our address in the universe, not just Earth, not just the solar system, but our position within the Milky Way, our place in the local group, our location in Laniakea, our relation to the cosmic web, our position inside the observable universe. We have been finding our bearings in the largest environment that can meaningfully be called an environment. And there is something about knowing that address, even imperfectly, even approximately, even knowing that vast regions of the cosmos remain unmapped and poorly understood, that changes the feeling of being here. The universe is not an incomprehensible void in which we have been somehow accidentally dropped. It is a place with structure and history and comprehensible laws, in which we occupy a specific, well-characterized location, and in which the processes that made us possible are understood, at least in outline. We know that stars made the heavy elements in our bodies. We know that a particular star, our Sun, was formed from a cloud of gas enriched by those earlier generations of stars. We know that the chemical and physical conditions on Earth were right for the development of life, and that life here has been running through increasingly complex forms for about 4 billion years. We know that the solar system formed in a stable region of the Milky Way, in a period when the galaxy had matured enough to produce the right conditions for rocky planets. We know that the Milky Way is old enough and stable enough to have allowed all of this to happen without catastrophic disruption. None of this was inevitable, but it happened. You are here because an enormous chain of cosmic events, stretching back to the first seconds of the universe, unfolded in exactly the way they did. And tonight, as those events recede further into the past and the universe continues its slow expansion, you are here to notice, to wonder, to feel, even briefly, the full scale of what contains you. That is not a small thing. That is arguably the most extraordinary thing we know of. Let's close this part of the journey with something simple and steady. The stars you can see tonight, or the stars above you, whether clouds permit you to see them or not, are not going anywhere on any timescale that matters to you or to anyone who comes after you. They are embedded in the disk of the Milky Way, moving through their slow orbits, stable in their nuclear burning, predictable in their motions. The universe is expanding. Yes, distant galaxies are receding. Laniakea is slowly dissolving under dark energy's influence. But none of that affects the stars above you tonight, or the galaxy that contains them, or the local neighbourhood that the Milky Way moves through. For all practical purposes, as for all purposes that apply to living human lives and all the generations to come, the sky above you is stable. The Milky Way will be there. Andromeda will grow imperceptibly closer, but on a timescale of billions of years. The cosmic web will shift, but slowly, slowly on timescales that make geological time seem brief. The universe you live in tonight is, from your perspective, the universe as it will be for all of recorded human time and beyond. That stability is worth noticing. It is the backdrop against which every human life, every civilization, every generation of inquiry and discovery takes place. The same stars that appear in tonight's sky appeared in the skies above the first astronomers who mapped the constellations, and above the scientists who first calculated the speed of light, and above the engineers who built the first radio telescopes, and above the astronauts who first travelled to the moon. The same Milky Way has been there for every act of human curiosity about the cosmos, unchanged in any way that matters by all the centuries of looking up at it. And now you are here tonight, in the long line of human beings who have looked up and wondered, adding your attention, your curiosity, your willingness to sit with the vastness and let it do what it does to the ordinary chatter of a restless mind. The galaxy is there, the universe is there, and you are here, inside it, quietly. There's one last thought worth bringing into this quiet space before the night deepens fully. We have talked about the observable universe, the sphere of space from which light has had time to reach us in the age of the cosmos. And we have noted that beyond that horizon, there is almost certainly more, possibly much more. Cosmologists working with the mathematics of inflation, the brief, extraordinary period of faster-than-light expansion in the very early universe, have proposed that the actual universe may be vastly larger than the observable portion. Some models suggest it could be millions of times larger. Others propose it could be infinite. The honest answer is that we do not know, and may never be able to know, because the regions beyond our horizon are, by definition, permanently beyond our ability to observe. There is a particular kind of peace in accepting that limit. Not every question needs an answer available tonight. Not every mystery needs to be resolved before you can rest. The universe extends beyond what we can see, and it does so quietly, without any requirement that we understand it completely. The horizon is not a wall and not a failure. It is simply the edge of what the speed of light and the age of the cosmos allow us to observe from here. Beyond it, the universe continues to be whatever it is, regardless of whether we are watching. That too is a thought that tends to settle the mind rather than disturb it. The world is larger than our knowledge of it, and always has been, and always will be. Knowledge grows, but the world it reaches toward grows too. There is always more. That has never been a source of despair for science or for the scientists who practice it. It is the source of the whole enterprise. The forward pull of the not yet known, the invitation of the not yet mapped, the quiet excitement of standing at the edge of the observable and looking in the direction of more. You don't need to go anywhere near that edge tonight. You can stay right here, in the warm and ordinary space of wherever you are, and simply hold the knowledge that you're inside something whose full extent you will never see and do not need to see. You are here. That is enough. That, in fact, is the whole point. The universe at night, the universe as it appears to us in the darkness, when the distractions of the day have quieted and the sky opens above us, has a quality of invitation that daylight doesn't quite carry. During the day, the sun's light dominates. The sky is a uniform blue, the stars hidden behind the brilliance of one particular star that happens to be very close. The scale of the cosmos is concealed behind the demands of the immediate, but at night the concealment lifts. The other stars become visible again. The faint band of the Milky Way reappears on dark evenings, and the imagination, loosened from its daytime obligations, is free to wander outward across the light years, free to contemplate the 2.5 million light years to Andromeda, the 500 million light years to the edge of Laniakea, the 46 billion light years to the edge of what we can observe. Free to notice that these numbers, enormous as they are, point toward something real, not toward abstraction, but toward actual space, actual stars, actual galaxies that exist whether or not we are thinking about them. The universe does not depend on our attention to be there. It was here for 9 billion years before the Earth formed. It was here for 4.5 billion years while the Earth cooled and life developed and eventually produced minds capable of noticing the universe at all. It will be here for billions of years after we're gone. It does not need us. And yet, it made us. Out of hydrogen and gravity and time, the universe constructed, through an extraordinary sequence of transformations, the conditions for thought, for curiosity, for the capacity to look back at the cosmos and say, what is this? How large is it? How old is it? What am I doing inside it? Those questions are not separate from the universe. They are part of it. The wondering is as much a feature of the cosmos as the galaxies are. And that thought, if it lands somewhere below the level of the intellectual and settles into the body, into the breath, into the quiet place where attention rests when it is no longer straining for anything, that thought is one of the gentlest, most spacious things you can take into sleep with you. The universe is incomprehensibly large. Our galaxy is incomprehensibly large. There is a kind of thought that doesn't need to be completed, that is best begun and then allowed to trail off into something softer, not a conclusion, but a slowing, not an arrival, but a gentle dissolution of the effort to arrive, and that is exactly the kind of thinking that scales like this invite, eventually. You have spent time tonight moving through measurements that the human brain was not designed to hold. From 100,000 light years to 10 million to 500 million to 93 billion. From a few hundred billion stars to 200 trillion galaxies. From the here and now to the 13.8 billion year old beginning of observable time. And through all of it, the aim has not been to make you hold all of this information simultaneously in focused attention. The aim has been something more like what happens when you read a beautiful description of a landscape you have never visited. You don't remember every detail, but something of the mood of the place stays with you. Something of its scale and quality settles quietly into the background of how you feel. The universe is large, the galaxy is old, the stars are steady, the space between them is vaster than anything we experience in daily life. And you are here, just here, in the middle of it, warm and breathing, your attention beginning to soften at the edges the way it does when the body starts to suggest that thinking is optional now, that resting is available, that the questions can wait until morning because they will still be there, and the universe will still be answering them in its slow, unhurried way. The Milky Way is not going anywhere tonight. Andromeda is not going anywhere in any timescale that applies to you. Laniakea continues its slow, geological drift toward the Great Attractor, and will continue to do so for 1 billion years, imperceptibly, without urgency. The cosmic web stretches across the observable universe in its filaments and voids, exactly as it was before you started listening, exactly as it will be when you wake up tomorrow. The universe does not require your attention to continue being the universe. It is completely, entirely fine on its own, and you can rest in that. Not because the universe is indifferent, though at one scale of description it is, but because its indifference is of the kind that allows you to put down the effort of trying to manage it. You are not responsible for the universe's trajectory. You're not required to worry about what happens to the Milky Way in 4 billion years. You're not asked to solve the dark matter problem tonight. You're simply here, in a galaxy, in a universe, for this particular stretch of time, and the universe is perfectly fine with that. It has been making room for you, at the physical level, since before you were born. The atoms in your body were assembled from material that the stars made. The planet beneath you formed from the same cloud of gas and dust that made the sun. The solar system found a stable orbit in a stable region of a stable galaxy, at a stable point in cosmic history. All of that happened without any intention of producing you specifically, but it produced you nonetheless. And here you are. Let that be restful. Let the scale of it be not a pressure, but a release. The universe is large enough that your particular weight in it, your worries, your uncertainties, your unfinished business, is small. Not meaningless, small. Held inside something large enough that the smallness doesn't diminish you. It includes you. If you've drifted at all, if your attention has softened and the images have grown less sharp at the edges, that is the right response to what we have been describing. The universe does not demand focus. It invites it, and then it absorbs it. The way a large body of water absorbs the force of something dropped into it without registering the impact beyond a moment's ripple. The stars above you, wherever you are, whatever the weather is doing tonight, are the same stars that have risen and set over every human life ever lived. Every person who ever looked up with the same combination of wonder and smallness that the night sky tends to produce was looking at the same galaxy you are part of. The Milky Way was there when the first of our kind made marks on cave walls depicting their observations of the sky. It was there when the first astronomers named the constellations and tracked the movements of the planets. It will be there, largely unchanged, when the last question tonight is set aside in favour of sleep. The universe is patient with the questions we bring to it. It does not demand that we understand it completely. It does not require that we get the numbers exactly right, or that we hold the full scale of it in attention without flinching. It is simply there, existing in the way that only things of cosmic age can exist, with a steadiness that has nothing to do with effort, an endurance that has nothing to do with will. You can take that steadiness for yourself temporarily, not because you are as large as the universe, but because you are part of it. The same material, organised differently, the same laws, operating at a different scale, the same expansion, playing out in the space between your thoughts as you begin to let them go. The galaxy is vast, the universe is vaster, and you are here, gently, inside the smaller of those two enormous things, resting. The night is holding you, the universe is holding the night, and everything is exactly as large as it has always been, steady and quiet and full and dark and full of stars beyond counting, beyond naming, beyond needing any more words than that tonight. Let the stars do what stars have always done when people needed to sleep. Let them simply be there, in the background of your breathing, in the sky above whatever roof is above you, in the incomprehensible distance that is also somehow home. That's enough for now. That's everything.